Let's go for a walk, Tom. Every morning, Tom walks along a straight road from his home to a bus stop, a distance of 400 feet. The graph shows his journey on one particular day. Let's just talk. Let's just look at this, not even look at the questions yet. So here goes Tom. Tom's walking, and he's going to walk a distance of 400 feet from his house, and this is his time in minutes. And as he walks, he is walking from home. So like at this point, which is 1 minute in, he is 250 feet from home, right? And then he's going this direction. So his distance from home is decreasing. So he's getting closer to home, like he forgot something. He didn't make it all the way home, obviously, because otherwise the distance would be 0. Maybe someone met him halfway and brought his lunch. I don't know. And then he heads back. And now he is at the bus stop. And he's waiting. How do we know he's waiting? Well, I don't know what he's actually doing, but he's standing still. He is not moving any distance from home. Now, we could say that he's walking in an exact radius around his home, but he is not traveling any further from his home or towards his home at that moment. All right, so we want to find Tom's average velocity on the time interval from 0 to 2 minutes. Whoa, what? What in the world are we talking about? Okay, average velocity, I just basically want to know, on average, how fast was he going? Now, in this lesson, I'm not going to get into too many specifics of velocity versus speed and that sort of thing. There are definite differences between them real quick. Speed is how fast you're going. Velocity is how fast you're going and what direction you're going. So like positive velocity, negative velocity, positive. So the direction's implied in there. So with velocity, this is technically going to be traveling away, but it's going to be worked out in the process of doing this. You're going to see this kind of computation a lot. Let's just write it in red because it's important. The distance that he traveled was 400 feet. And it took him 2 minutes to get there. So Tom averaged 200 feet per minute. Now clearly, he was going faster at some points than others. I'm not counting this, that's beyond 2 minutes. But at one point he was being counterproductive. But it's all, it took him 2 minutes to go 400 feet. So 200 feet per minute. He went even further on foot. And that's going to come in really handy in a few units. He went even further on foot. He traveled further than 400 feet. But his getting to his destination took him 2 minutes, and he traveled 400 feet in that direction. Okay? Well, he traveled more than that. He had to backtrack. Describe Tom's journey on the interval from 0 to 2.2, including details about how fast he walked in the direction he was walking. Really quickly, just going to make some stuff up. So Tom is walking at this speed. I say this speed, and I'm referring to the slope. So for the first minute, Tom walked. Okay, which direction is he going? Well, he's going away from home. Away from home. All right, how fast is he going? It took him 1 minute to go 250 feet. So he's traveling 250 feet per minute. 250 feet per minute. So for the next 2 blocks here, which not 2 city blocks, but 2 units, 2 markers on our x-axis, our time axis, 0.4 is the equivalent. For the next 0.4 minutes, Tom walked home, towards home. For the next, I might run out of room here, next 0.4 minutes, we can convert that into seconds if we want, let's not. Tom, all of a sudden he's lowercase, he became less important, I don't know, walked toward home at, okay, now what's his speed? He is traveling, let's see, he went 150 feet in 0.4 minutes. So 150 feet in 0.4 minutes, 375 feet per minute. 375 feet per minute. All right. He heads back towards work or towards the bus stop. All right, how long did this take? So 0.2, 0.4, 0.6. For the next, my handwriting is getting terrible, 0.6 minutes, Tom, outside the box here, walked away from home at, okay, how far did he travel? And how long did it take him? I hope you realize what we're doing. We're dealing with slope. Now, that doesn't relate to what's going to happen here, but we're going to have the conversation about slope as a rate of change on the front side of the notes. And then when we get to the back side of the notes, the conversation shifts to finding the slope at a specific point. Okay, and that's going to open up a whole big bag of calculus. It's going to be beautiful. So let's see, Tom walked 0.6 minutes and traveled 300 feet, almost at 300 miles. He's looking at 300 divided by 0.6 is going to be 500. So 500 feet per minute. Whew. Good luck reading that. At 2 minutes to 2.2 minutes, and that's as far as we needed to go. 2 minutes. Tom, I'm going to just assume that he stood still. He's not traveling any distance from home. Tom stood still. Okay, now that is a pretty safe assumption, but here's what I'm thinking, because I'm getting all mathematically technical in my head. I'm overthinking it. Here's home. Here's Tom. If Tom travels in this circle, he's not getting closer to home or further from home, but that is not what happens at a bus stop. So he's just waiting. All right, that's where that comment comes from. Tom was traveling the fastest during which time interval? Okay, well, let's look at the speeds here. And fastest, that's the speed issue. It's not which direction is he traveling. So that's the speed issue. So 250, 375, or 500. Well, 500 obviously is the biggest, so he's traveling the fastest during that time interval. So the answer to the question is a time interval. One of the things we're going to have to do in this class is interpret questions correctly and answer what they asked. I cannot answer this question with 500 feet per minute. It can be in my answer, but that's not what they asked. He was traveling the fastest during which time interval? And he was traveling the fastest. I'll put it as a complete sentence. Tom was traveling the fastest for, and I'm going to write it as an interval with like inequalities and everything. So from here to here, this is where the 500 feet per minute came in. And that is at 1.4. 1.4 less than or equal to t less than or equal to 2. Now we can make arguments about whether we should make them equal, the 1.4 and the 2 or not, but let's not get too technical with it.